Hello viewers, welcome back to the course on scientific computing in MATLAB. So, today we will going to use the finite difference table to approximate the value at any x in between the given values. So, let us continue with the finite difference table. So, let us do one question based on the previous lecture. So, I want to locate the error in the following data and correct it. So, that is the question. So, let us I have the value, this is the value is given to me x and y. So, x is -1, 0, 1, 2, 3, 4, 5, 6, 7, 8. So, this is a total 10 values and the y value is given to me 7, 5, 3, 7, 25, 57, 115, 203, 327 and 493. So, if you see from this table that it is giving me the expression that this value is satisfying a function which is an increasing function. So, that only we can say from this looking at the data. So, let us take the first difference. So, the first difference I am taking the forward. So, this is 5 minus 7 minus 2, 3 minus 5 is minus 2, 7 minus 3 is 4, then 25 minus 7 is 18, 57 minus 25 is 32, then it will be 58, then it will be 88, then it will be 124 and this is 166. So, this value is the first difference. Then I take the second difference. So, second difference will be that will be 0, then 4 minus 2 is the 6, this is 14, this is again 14, this is 26 and that is 30, that is 36 and this is 42. So, I am writing here this value in between, this value in between. Now, I am writing this value in between these values. So, that is the way we can write the table. Then I will take the third finite difference. So, this is 6 minus 0, it is 6, 14 minus 6 is 8, then it is 0, then it will be 12, then it will be 4, it will be 6 and then it will be 6. Then I take the fourth difference. So, it is 8 minus 6 is 2, 0 minus 8 is minus 8, 12 minus 0 is 12, 4 minus 12 is minus 8, 6 minus 4 is 2 and this is 0. Now, from here we can see that the pattern looks like the binomial pattern. So, from here I will just stop here and I will see that what will happen in this case. I am getting the errors. So, if you see from here, this is 2, 2, minus 8 and 12, and if I add all this error together, so it is 12 plus 2 14 plus 2 16 and this is minus 8 and minus 8. So, it is 16 minus 16, so 0. So, that gives me that error in this case, because we have seen that the errors in any of the column is 0 if I take the sum of all the errors and they follow the binomial fashion. So, in this here, if I stop here and then I will see that my error is, so I just take the 2 common, then I can write this is 1 minus 4, 6 minus 4 and 1, and from here if I see that I can write that this is same as 1 minus 1 raised to power 4. So, if you see from here, the coefficients will be, so I can write from here x plus y raised to power 4. So, this is x raised to power 4 plus 4 c1 x cube y plus 4 c2 x square y square plus 4 c3 x y cube, and in the end we will get y 4. Now, if I put, so this 4 c1 is 4, this is 12, this is 6, this is 4, and if I put x is equal to 1 and y is equal to minus 1, I will get the same the coefficients. So, this coefficient will be there. So, based on this one I can see that this is the error following the binomial pattern. So, from here I can say that my error epsilon is 2. So, this is the error I have taken. So, now from here I can say that now I want to see that also that the error grows symmetrically. So, one above and one below. So, from here you can see that if I choose this value 25, it will go this to this, then from here it goes this to this value. So, this goes here and then this goes here. So, like this one, then it will go this way, this way, then it will go like so, like this way. So, that is the my error. So, if from here I can see that my error will be definitely in this value, and from here I can say that my, so it is value is y minus 1 0 1 2 3. So, y 3. So, error is and the y 3. So, from here I can say that this is equal to, the value is given to me y 3 plus epsilon. So, from here I can write that y 3 plus epsilon is 25, and from here my y corrected y 3 will be 25 minus epsilon. So, it is 25 minus 2, that is 23. So, this is the corrected value of y 3 is 23. So, based on that the pattern of the errors and the symmetriness of the error, we can find that the error is there in the value of 25 and we can correct it, and this corrected value is 23. So, here we have used the finite difference table. Now, after doing this one, we will discuss very important theorem. So, this is Weierstrass theorem of approximation. So, it states that any function f x which is continuous in the interval a b, so it is continuous in the interval a b, can be approximated by a polynomial, that is p x, uniformly over the interval a b, such that for a positive epsilon, where epsilon is very, very small, such that if I take the difference f x minus p x for any x in the interval, that I can make less than epsilon for all x belongs to a b. So, in this case everything depends upon that how small the epsilon I am taking. If I choose very small epsilon, then the polynomial will be of higher degree, and then this difference can be made less than epsilon based on the value of given epsilon. So, that is the Weierstrass theorem of approximation. Now, we will use this theorem later on. So, now I will write down the interpolating polynomial. So, let us do it Newton's, or we call it Newton Gregory forward difference formula. So, suppose we have data, and data is given to me in the form of xi coordinates and yi coordinates. I is moving from 0, 1, 2 up to n. So, total n plus 1 points are given, okay. And so, suppose we have this data and xi plus 1 minus xi is equal to constant h. It means that equi-space data, equi-space values. Then, so I can write this xi as x0 is less than x1 less than x2 less than xn. Now, we want to determine the value of y at any point x that belongs to this interval x0 to xn. So, this is the open interval I am taking, because if I take the closed interval, the value at x0 and xn is already known to us. So, I am taking the open interval. Now, I want to determine the value of y at any value x in the open interval. So, what we represent now? So, let yx gives me the exact value of y at x and y at subscript x. So, that is the computed value. Of y at x. It means that I have some data like, so some data is given to me, this value, this. So, like this value is given to me, and based on this one I will write a polynomial, interpolating polynomial. So, this is suppose my interpolating polynomial. So, this is my interpolating polynomial, and now I want to find the value of y at any x. So, suppose this is my point x0, y0, and this is my xn, yn. So, my value is given to me at this point, this point, this point. Now, I want to find the value of the function y at any x in between somewhere. So, my x can be here, it can be here, it can be here, here, any value I can want to find, and yx is the value exact value of the function at this point, and y subscript is the computed value of this one. So, this is my interpolating polynomial. Now, from here we also know that y at xi at the given value, that is same as y xi. So, this value are same, because I know that at the nodal points my function is also passing from the given data points, and my interpolating polynomial also passing from these data points. So, this is true for all i's, that is 0, 1, 2 up to n. So, this is true that computed value is same as the exact value. So, this is one of the things we already know from the interpolating polynomial. Now, I want to write yp is equal to x. So, this y I write a x is equal to x naught plus ph. I introduce a variable p, h is already known to me, and x naught is the initial point of the data, and I call it x p, or from here I can say that my p is equal to x minus x naught by h. So, this p I am introducing. So, this now I want to find the value of the function at x. So, let us do this one. So, I want to find y is equal to x. So, y is equal to x is y x naught plus ph, and this one I can write as a shift operator p y at x naught. So, y at x naught is y naught. So, I can write as a e p y naught. Now, from e p I know that this can be written as 1 plus y naught, because we know that e can be written as 1 plus forward operator. So, I am putting this value. Now, from here I am expanding this one using the binomial expansion. So, from here I can write this as 1 plus p del plus p minus 1 by 2 factorial del square p minus 1 p minus 2 up to 3 factorial del cube and so on. Now, I know that if I have the n plus 1 number of points, then the nth finite difference and nth difference operator will be a constant value, and the next value will be 0. So, it will go up to the p minus 1, so p minus 2 up to p. So, I suppose I have this value k minus 1 divided by k factorial del k. So, this my polynomial is going up to the kth finite difference, and this is equal to y naught. So, this k is always less than equal to n. So, definitely this polynomial will be a terminating polynomial, and it will terminate. So, let it terminate after the k finite difference, and that k is, I know that it will be always less than equal to n. So, from here I can write, now I can take the y naught, apply this operator on the y naught. So, it will be y naught plus p y naught p minus 1 by 2 factorial delta square y naught and so on, and in the end I will write p minus 1 p minus 2 up to p minus k minus 1 by k factorial del k y naught. So, this is my polynomial. I am getting the polynomial in P. Now, the problem is that on the left side I have the y at x, and the right hand side I have all the terms in terms of p. So, that we can convert into back into the x form. Now, from here I can write, so this is my 1. Now, p can be written as p is equal to x minus x naught by h. So, p minus 1 can be written as x minus x naught by h minus 1. So, this is x minus x naught minus h by h, and that can be written as x minus x naught plus h by h, and this is x minus x 1 by h. Similarly, I can define p minus 2. So, you can see that it will be x minus x naught by h minus 2, and this will be x minus x 2 by h, so on. So, this way we can write all the terms in the terms of p, and from here my equation number 1. So, from here we can write yx is equal to y naught plus this is x minus x naught by h del y naught plus x minus x naught x minus x 1. So, this is coming x minus x naught x minus x 1 by h square into 2 factorial, and in the end I can write this as x minus x naught x minus x 1 up to x minus x k minus 1 divided by h raised to power k factorial del k y naught. So, that is the interpolating polynomial using the forward difference operator del. So, that is the value, that is the polynomial we are getting. Now, if I am able to find this polynomial, then you just put the value of any x here, and I can get the interpolating value of that using this equation number 2. So, that is the, I can write it a interpolating polynomial using forward difference operator. So, now the question is that how we can use this one. Now, if you see from here, I need to find what is this one, what is the second difference, and what is the k difference. So, to implement this equation number 2, we have to first make the finite difference table, and from the finite difference table we have to calculate the value of these operators, these differences, and then substitute that values, putting the value of all these data points x naught, x 1, x 3. Then from after substituting all this value, you will get the polynomial of degree. So, this from here I can say this is the interpolating polynomial using forward difference of degree. So, from here you can say that the degree will be, I am going up to x k minus 1. So, degree will be k. So, maximum it will be k. So, its degree will be, I can write less than equal to k. If I stop here, its degree will be only 1. If I stop here, its degree will be on maximum up to 2. So, I am going up to k, its degree will be always less than equal to k, because it may happen that the coefficient becomes 0. So, in that case its degree will be less than k, otherwise it is the kth degree polynomial. So, this is called the interpolating polynomial. Now, the question is that when I can apply this Newton forward difference. So, this is a Newton forward difference formula. So, when I can apply? So, I can apply these values whenever I need to. So, I know I have a values, suppose I have a value. So, this is the data given to me x naught, x 1, x 2 up to x n. So, I can apply this value whenever I want to approximate the value at some x and x is lying somewhere here, because in that case if it is lying here, then I can use all these values, whatever the values. So, this is the x naught. Similarly, I can have value y naught, y1, y2 up to yn. So, if I want to approximate the value of x somewhere in the middle or somewhere in between the x naught and x1, then using the finite difference operator I can use all the values. So, because from the previous lecture we know that this value will move like this one up to the kth finite difference. So, in that case I can use all this value and my approximation will be better. But suppose that my x I want to find and x is lying somewhere here. So, in that case what will happen? I can use only this value and all the value below this one. So, below this one will be very less values. So, in that case in my polynomial, whatever the interpolating polynomial we are talking about, the degree of that polynomial will be very less as compared to the degree of the polynomial when the value of x is lying here. So, in that case the approximation will be very not as good as we are getting in the case of the value of x lying here. So, everything depends that where the value of x is lying. So, in this case our value of x is lying here somewhere in the top of the table. But sometime it may happen that I want to find, I have the values like this one x0, x1, x2 up to xn, and my x is lying not here, but it is lying here somewhere. So, that is my x. So, in that case what we will do? We shift this one and we call it x. So, x1 I call it x0 and this I will call it x minus 1, and then I will call it x1 and this will be x n minus 1. So, in that case we just shift this indexes so that this becomes the x naught, and then after this I can use the finite difference table, and then I can use all these values corresponding to this line and putting this here in this equation and get the interpolating polynomial. So, from here I can say that to implement this formula number 2, I can write that we try to retain as many differences as possible for better accuracy. For better accuracy, number of differences decreases as we go downward in the finite difference table, as we have just discussed. So, therefore, this formula is suitable only for the values to be computed near the upper end of the table. So, that is there, and the second one is, I can write here the next important point is that we can shift the origin so that the value of p is lying between 0 and 1. Okay. So, this means that I just, for example, I have taken here that my x is lying here. So, I am shifting this x1 to x0 and x minus 1. So, in that case my value the p will be always lying between 0 and 1. So, we shift this means that it is not necessarily to have first tabular point as x0. It may start from negative indexing also, like it start from -2, x -1, then x0, then x1, like this one. So, in this case I have shifted 2 times to make this x0. Earlier it was x0 here, but I shifted it to x0 here, and then the previous values I call it x -1 and x -2. So, this way we can shift just to choose that the value of the p is lying between 0 and 1. So, I should stop here. So, today we have discussed that how the error propagate in the finite difference table, and then we have discussed the Newton forward difference formula to approximate the value at any x, and that x lies in the upper part of the finite difference. So, we will continue with this on the next lecture. So, thanks for watching. Thanks very much.